What do you
Yeah, can you share it again?
Yes, yes, that's what.
Okay, this one.
Yes, yes. The full screen. Yeah, do that. And I want to hide this, right?
Yes.
This is okay?
Not change slide. Which one? Slides change?
This, yeah.
Okay.
You can use this one, right?
Yes.
Yeah, yeah. Yeah, yeah, sure.
Hello everyone, welcome to this week's string seminar. Today we are very happy to have Seok Kim from Seoul National University, and he'll tell us about aspects of black hole cohomologies. Cool.
Thank you very much. I'm very happy to visit Bangalore and ICTS. It happens to be my first time to visit this city and the institute. It's my shame, but I really like this institute, the atmosphere, especially the mild climate, so I feel I should visit again. So I'll today talk about some problem that I've been thinking about for some while, but most extensively during the past 2 years, about a modest program to understand some aspects of the microstates of black holes in ADS-CFT correspondence. So I'll explain to you the problem. So roughly the talk will be based on some of the many papers that I have wrote during the past 2 years with these collaborators in various collaborations. And in the last part of the talk, if I will have time, as an application of this program, I'll talk about something which is closely related to the recent progress on the hairy ADS black holes. Mostly, these are the papers that I'm working with, basically with the TIFR group, also with some of my Korean colleagues. So, the general question that I'd like to understand better is to sort of construct and better characterize the individual microstates of the black holes, which hopefully will account for and contribute to the area law, this Beckstein-Hawking entropy of the black holes. Okay. Most concretely, I would like to better understand this problem in the context of the black holes in ADS 5 times S5 using the holographically dual maximal super-Yang-Mills theory. Okay. But constructing a microstate which accounts for this at given charge and energy requires you to do generally a strongly interacting calculation in the QFT, which is generally hard. You might think that studying BPS black holes, preserving some supersymmetry, might help, because the microstate that I'm going to construct will also preserve some supersymmetry, and supersymmetry often does good jobs. But it turns out that this question of constructing the exact energy and charge eigenstates from the conformal field theory turns out to be hard, even with supersymmetry, presumably because the preserved amount of a supersymmetry by the black hole is small. Okay? So today, I'll be explaining to you and provide you a partial solution of a very modest version of the above construction program. Okay? The sense in which the today's talk will be modest will be gradually explained during the talk. But to highlight some aspects, I can mention two things. So instead of doing the calculation of quantum field theory in strong coupling, we will study the states preserving the same supersymmetry as the holographically dual black holes in the weakly coupled regime. Okay? And I'll be studying it in the form of a certain cohomology problem, which will make the problem more modest, okay? But something concretely calculable. Secondly, we'd eventually want to understand this problem in large N gauge theories, okay? When the rank of the gauge group is parametrically large. Somehow this turns out to be difficult, making the problem difficult at many places. So we want to study this problem at low rank, like SU2, SU3, SU4. Modestly, this will be an intermediate step towards getting to a parametrically large N gauge theory. But the result at these lower ranks already, I'll try to convince you, shows qualitatively exciting, intriguing features. I mean, some features of these low rank cohomologies show some qualitative features very reminiscent of black holes. So I'll try to explain to you that as much as the time permits. So today's contents are as follows. Okay? First of all, I have to explain the problem. That will be 1/3 of the talk. And I'll be presenting you the new states or operators that I found in this program. Okay, so I'll just present you the results. In the course of finding, there's lots of detailed techniques and tricks involved, but since I don't think that will be giving us a nice physics intuition at this moment, I'll be skipping all these and just present to you the results we found. Finally, if time admits, I'll explain to you some applications of the new findings. And the topic that I'd like to focus on today is the no-hair theorem of the black hole versus the existence of hairy black holes in ADS. Okay? I'll be trying to see some aspects of this in the low-rank, weakly coupled microstates that I've constructed. I have this plan, but I mean, if any of you are unfamiliar with this topic, you can slow me down at any stage, ask many questions. I mean, that will be okay. I don't think I have to cover everything. Maybe the last part I just can highlight in the last 5 minutes, so feel free to ask questions, please. Okay. So I'll explain the problem in the next few slides. This slide is the most technical one. I included all the details because I wanted to be as sort of precise in the notational sense, but you don't really need to know everything, little bit of these things to follow it. I mean, I think remembering certain keywords and following the basic flow of logic will suffice, I think. So the theory of my interest is SUN, maximal super Yang-Mills. Let's say you take a Euclidean Yang-Mill theory on R4, okay, flat R4. All the fields in maximal super Yang-Mills are in the adjoint representation, traceless n-by-n matrices. And in the n equal 1 superfield language, they arrange themselves into 1 vector multiplet and 3 chiral multiplets. Okay? There are some supersymmetries preserved. And the interest of in this program is to study the local operators of these, made out of these elementary fields on R4. So we pick an origin of R4, study some operators located there. And this local operator is interesting because the CFT enjoys what's called the operator state map. So this local operator maps to the physical states propagating on this hypercylinder, which is the conformal boundary of the global ADS5, which will be the playground of studying ADS5 black holes. Okay? So I'll be studying local operators on R5, and I'll be studying the gauge invariant local operators, which preserve some supersymmetries. Okay? And the supersymmetries that is demanded to annihilate the local operator of my interest is picked as follows. It's exactly the supersymmetry preserved by the corresponding black hole. So I pick one of the Poincare supercharges carrying particular indices and one of the conformal supercharges. And these two turn out to be Hermitian conjugate to each other in what is called the radial quantization, I mean, in this scheme. And I demand my operators be annihilated by these two supercharges. Yeah. Yes. Okay. And as I told you, I'll be discussing an easier problem. Rather than studying the spectrum at strong coupling, I'll be studying this operators at weak coupling. So first of all, I studied the free theory limit. Okay? In the free theory limit, what you have to do to identify the full set of these BPS local operators is to first identify the subset of these fields invariant under these supersymmetries. For instance, taking this Q, the following subset of fields turn out to be invariant under this Q. And also, you can decorate these fields by a subset of derivatives, the so-called holomorphic derivatives on R4, which turn out to be respecting this Q. And this field can be dressed by acting any number of holomorphic derivatives. And this basically gives me the letter of constructing gauge invariant operators. Okay? And once you have these BPS fields and BPS letters, you form any gauge invariant. I mean, you contract the rows and columns in any way you demand, any way you like. You get a composite operator at the origin of R4, and they are all guaranteed to be BPS in the free, supersymmetric in the free limit. Because in the free theory, once you make a composite operator out of these elementary operators, they don't acquire anomalous dimensions. So in the free theory, it's just a combinatoric problem. Okay? So you can easily construct the supersymmetric states preserving these two in the free limit using these fields and derivatives, but it turns out that there are too many of them, okay? Giving almost no insights about the interacting quantum field theory spectrum. What we find by studying the BPS states I constructed is that at low energy, these operators shows more states than the low energy graviton states that we believe should be there according to the ADS-CFT. At high energy, they turn out to exhibit more states than what we expect from the Beck-Einstein-Hawking entropy of the black holes. So there turn out to be more states than we expect from ADS-CFT. So what happens is that if you turn on coupling constant, many of these free BPS states should turn out to be anomalous. Due to the coupling effect, a large number of free BPS states will turn out to be non-BPS, and the remaining subset will remain to be BPS. And I want to understand which subset remains BPS as you turn on coupling constant. I turn on coupling constant to be very small, okay? And for instance, I study the supersymmetry transformation of the following free BPS fields using the supercharge of the classical interacting Yang-Mills theory, okay? So many terms remain zero even after turning on coupling constant, but some terms are non-zero because you move from free to interacting theory. So the free BPS fields turn out to be non-BPS anymore in the interacting theory. Okay? So if the right-hand side is non-zero, they are always linear in G Yang-Mills because that's the nature of the free. That's the nature of the classical super Yang-Mills theory. Okay? So the supercharges acting on this subset of letters is in the classical Yang-Mills theory is linear in G Yang-Mills. If you anti-commute them, they give rise to the anomalous dimension of the operator, energy beyond the BPS energy bound, which is at order G Yang-Mills square, namely one loop. So using this supercharge at half loop, you can study the anomalous and non-anomalous operators at the one loop level. This will be my problem. Okay? Even though these right-hand sides of some fields are non-zero, if you multiply them and make a gauge invariant combination of them, this non-zero right-hand side might cancel. If that happens, they turn out to be the gauge invariant non-anomalous operator, BPS operators at one loop. Identifying these operators is the purpose of this program. Okay? This one loop BPS state problem can be reformulated as a cohomology problem. Okay? This reformulation can be made by noting that the supercharge used to define my BPS states are all nilpotent. They square to zero as part of the superconformal algebra. And the equation which defines our BPS states can be reformulated in this way. Okay? So these Qs are nilpotent Qs are formally taking the form of the exterior derivatives acting on differential forms. And this equation is formally taking the equation for harmonic differential forms. Okay? So using this formal analogy, what we appeal to is the one-to-one match between the spectrum of harmonic forms and the cohomology class with this nilpotent operator. Okay? So if you're interested in, the detailed form of the one-loop BPS operator, you have to just construct that. If you're just interested in the spectrum of the one-loop BPS operators, you can alternatively study the cohomology class of this classical supercharged Q. Okay? Note that although this problem is studying the spectrum at the one-loop quantum level, the cohomology problem is governed completely by a classical interacting field theory supercharge. Okay? So the n by n matrices, bosons and fermions, they're all classical. There's no quantum aspects in this final cohomology problem. You can just regard them as n by n C numbers or n by n Grassmannian numbers, right? Rather than quantum objects.
So is there a general proof of this? That
this one?
BPS spectrum is a classical cohomology class?
Yes, I think you can formally borrow what's called it, Hopf theorem or something, about the map between harmonic forms and Q cohomology class. Yeah, I think you can formally appeal to that proof and just borrow it to, yeah, this context.
So the extra states which are there in the field theory are somehow Q exact. Is that the...
They are either Q exact or not Q closed. In both cases, in the physical terms, they live to the non-BPS states. Yeah, yeah. Any other? Good. So I've explained to you the recoupling spectral problem of my interest. You may ask at this stage, what does it have to do with the strong coupling spectrum that I'm eventually interested in? Because I said I'm interested in understanding black holes, and holographically that should emerge as strong coupling of the quantum field theory. Well, simply, from almost 20 years ago, there's been a conjecture that once you have fully identified the spectrum of one-loop BPS operators, they will remain, at least their spectrum will remain unchanged as you change the coupling all the way to strong coupling. That has been conjectured by many people, mostly including Shiraz Minwalla and Suvrat also, Maldacena, and so on. So that was a kind of a conjecture or the hope that people had at that moment. There's no proof of that. There's some evidence, and there's an attempt to prove that one-loop BPS spectrum remains unchanged all the way to strong coupling. But I should say that it's still open. I mean, these authors have attempted to make some perturbative argument for the non-renormalization theorem. I think it's very, very impressive, but I also hear that there's some loopholes, so the situation is slightly unclear. What I should emphasize is that the spectrum is conjectured to be unchanged, but the detailed form of the BPS operator, of course, will change. I mean, it depends on coupling, but the existence of the states and the degeneracy of the states is conjectured to remain unchanged. Okay? A circumstantial evidence, partial evidence of this conjecture is the following. You know, there's an index, a very nice index, which counts these cohomologies that I've just explained to you. And recently, in the past few years, the index of these cohomologies has been studied very extensively in the large N limit. And this index of these cohomologies has been shown to capture the leading black hole entropy successfully. So at least we can say from this index that many of these one-loop cohomologies, if not all, should be protected because it matches with the spectrum of the strong coupling object, which is the black holes. Okay? So with this kind of circumstantial situation understood, I'm going to study the one-loop BPS spectrum in terms of this cohomology. I mean, hoping that it will tell us useful lessons about the physics of black holes. Okay? Okay. Before getting into the real details, I should explain to you that there are two different types of cohomologies. Okay? Basically, one is what we have been well known for several decades, and another, all the rest, that has been unknown until 2 years ago. Okay? Physically, the spectrum of these cohomologies that have been well known are called the gravitons, you know, and all the rest, I mean, often I'll say these as black hole cohomologies, hoping that many of them will correspond to the microstates of black holes. It might be abusing the terminology black hole, but very often I'll call these black hole cohomologies. Sometimes I call them non-graviton cohomologies and so on. I mean, there are various ways of calling these two classes in the literature. And very mathematically and neutrally, some people call these monotone cohomologies. They call these fortuitous cohomologies. But I mean, I'll stick to this intuitive terminology at the risk of abusing the terminology black holes. So what does graviton cohomology mean? In the large N limit, the physical notion of graviton cohomology is very clear. It's mapping to the BPS states corresponding to the supergravitons, which account for the low energy spectrum at large N. Okay? Having in mind application to the finite n cases, I pragmatically define the graviton cohomologies as follows. In large n, it completely agrees with the supergraviton that you may be knowing. So first of all, you construct the cohomologies using the single trace operators only. Okay, so use the BPS fields in the free theory and construct single trace operators and seek for the one loop cohomologies using single trace operators only. Okay, there everything is understood. Okay, and the structures are operators are organized into the multiplets of this PSU 1,2/3 supergroup, which is a sub-algebra of this full superconformal algebra of the Yang-Mills theory that commutes with the two supercharges that I picked to define my cohomology problem. So this is the symmetry of the cohomology problem. Okay, so all the BPS states should arrange themselves into a representation of this. The primary of this single trace graviton cohomologies is just made of scalars. It's just well-known chiral primaries. Scalars completely symmetrized inside the trace. And the remaining states, including fermions and field strength, can be constructed by acting the generators of this as a descendants. Roughly speaking, this is single particle gravitons. Then you can just multiply them. You know, the cohomology, by the nature of cohomology, you multiply two cohomology, they become another cohomology, just because of the fact that the operator Q satisfies the Leibniz rule. If individual operators are closed in Q, multiplication is also closed in Q. Okay? So multitrace gives them another large class of cohomologies. Physically, they correspond to multi-graviton states, multi-particle states. Okay? At finite n, the same definition above gives rise to a class of well-known cohomologies. So the definition goes in the same way. The subtle issue is that the following definition is redundant or giving you an overcomplete set. Okay? That's because of the fact that at finite n, the number of independent cohomologies among those stated here reduce due to the trace relations of the finite n by m matrices. For instance, if you work with an SU2 matrix, 2 by 2 traceless matrix, trace of matrix fourth is proportional to trace of matrix square over square. So the multi-trace cohomology and the single trace cohomology can be redundant. Okay? So this redundancy is also very well known in the gravity dual. It's often called the string exclusion principle. You know, if you give too much energy to a graviton, it is well known in string theory that they polarize to brane-like objects. And the brane spectrum of independent states becomes reduced compared to the naive estimates based on the point particle picture. So even this finite and reduction of degrees of freedom is precisely encoded in the gravity duals. So I think they well deserve to be called the graviton cohomologies even at finite n. Okay? So these are just well-known things, you know, and all the rest I'll just casually call black hole cohomologies. Okay? And I'll try to discover some of them to you at low ranks and studies of physics. Yeah.
So there's no positive characterization of all the rest.
That's,
I mean,
there are some, yeah. If you want some mathematical characterization, I can give you an alternative definition of these two. As I told you, I mean, it's Chiming Chang and the collaborators call this first class monotone cohomology. Monotone cohomology means that this is, I mean, it has to do with the Q closeness. The operator becomes Q closeness at any n. So you prepare an operator, and there's a family of operator with SU2 at n equal 2, 3, 4, 5. And if the operator is Q close for any n, it's called monotone. Fortuitous means accidental or something like that, right? The other cohomologies are characterized by a class of operator defined at any n, but which becomes closed only by using trace relations. So it may become closed at low n, but if you increase the n, maintain the form of the operator, it suddenly becomes non-Q closed, right? And that sort of characterizes gravitons and black holes well, because if you fix the energy level, I mean, if you fix the energy form and just increase the energy, increase the n, I mean, eventually the given operator will run into a low energy spectrum, right? And that should be a graviton, right? So that characterizes monotone operator. But the black hole operator doesn't behave like this, right? You know, the energy of the black hole states should scale with n. So that's a mathematical way of characterizing it better, yeah.
correct that while defining this monotone homology,
Yeah.
you just ignore the stringy exclusion principle altogether?
Stringy, okay. So this exclusion principle and trace relation will have to do with after you get a collection of states, estimating which is independent, which set of them are independent. At that stage, string exclusion principle will apply. But just preparing an operator and checking whether it's Q closed or not, I mean that can be just done without appealing to any trace relations.
But when you define the monotone,
yeah.
Do you take into account the stringy exclusion principle, or?
Well, at the moment of estimate how many of them are independent, then trace relation will have to be taken care of. And by that you include the giant gravitons. Yeah.
Perhaps, is this correct to say that if you think of these trace relations as some kind of thing that we are quotienting out by?
Yes.
In some sense, the gravitons, you have some inherited sectors, but then the black holes are some kind of twisted sectors after you
Quotienting out.
You quotient by the trace relations. I'm thinking of.
Yeah, quotienting out the gravitons by trace relations. Yes.
So there are certain gravitons you project out.
Yes.
We quotient.
Yes.
We project out some things.
Yeah.
But then sometimes you also get new states.
Yes, those are the black hole states. Yeah.
So sometimes again the trace relations are imposed in the sense that on the gravitons you still call them gravitons. The inherited sectors are still gravitons.
Yeah.
The twisted new states are all black holes.
You think there may be relation to the projected out things and the new things appearing?
Yeah, in the sense that it's because you're projecting out by trace relations that
using the same relation you can have new states.
You have new states.
Actually, that is also true. I mean, I don't think that's the most general mechanism of constructing new states, but certainly it's a mechanism which can construct new states. Actually, we extensively use that idea to construct black hole-like operators, some class of them. Because, so that's one of the techniques we construct new operators. So if you make a polynomial of graviton operators, we know that is vanishing in the cohomology. And it means that by using the trace relation, it becomes Q-exact, certain polynomials of graviton, and we don't count them independent. But once you have identified a polynomial of graviton being Q-exact of certain operator, polynomial of Q-exact operator using trace relation, you can use that element to construct a new black hole-like operator. Because, this trace relation of gravitons are happening in various layers. Some polynomials of gravitons, trivial combination, give rise to Q-exact terms, but another bigger combination of gravitons, polynomial of gravitons, are giving exact cancellation to 0. Okay, so you form a trace relation giving a polynomial equal to Q-exactness of something. You form a bigger polynomial including them, so that the left-hand side polynomial vanishes. That gives rise to your new Q-closed operator, and that's one of our ansatz of constructing new black hole-like cohomologies for SU2 and SU3. That's certainly true. So it's, in a sense, that might look like a twisted sector, as you say, but I think the state that you can construct in this way is much less than what we generally expect, because gravitons are basically diagonal polynomials. Black hole states are much more than that, right? So I think this will be one way of constructing subset at most with that.
Or maybe to hazard another way of thinking about it, and you should say whether it makes sense. Can one think of trace relations as some kind of large gauge transformations of some kind, and that you have, I mean, I don't know, of some bulk symmetry, as yet unknown bulk symmetry.
Oh, because you're modding out something.
And that you impose there are small gauge transformations, which are kind of the ones that correspond to the standard gauge invariant ones, like the graviton cohomology or the monotone cohomology, and then maybe the other ones are things which are invariant only after you take into account some large. Would that kind of, that's a bulk, I mean, it's a
that really makes
potentially
sense.
bulk.
Yeah, that really makes sense, because most of the non-trivial trace relations are some combination of operators being Q-exact, so trivial in the cohomology. And in this cohomology problem, modding out by Q-exact terms, it's really like cutting off the gauge copy to have the cohomology class. So formally, definitely it's true. It will be great if we can give more physics to it. Yeah, but at the formal level, definitely that's true. It's
some bulk interpretation to it.
Yes.
This is all in the side of the gauge theory.
Yes, that's true. That's true. Yeah, we can think about that from this graviton sector and so on. Yeah, that's interesting. I don't have interesting things to say, but I'll have that in mind. I'll have that in mind. Thank you. Thank you. Okay. Any other questions? Yeah. As I told you, I don't have to finish everything, so please. I think understanding the question is most important, right? Yeah. So with this understood, I mean, these kind of objects in the construction problem of cohomology will just be rubbish or noise in a sense. Yeah. Even after I construct something which looks new, I have to struggle to show that it doesn't belong to this class. So I've explained to you what the noise information should be. And with all the rest, I'll study the remaining operators, cohomologies, at low ranks because of my limited computational power, SU2, SU3, SU4 with, yeah. And as I told you conservatively, this will be a modest step towards going to the large N quantum field theory and cohomology. But hopefully, we may wish to identify and study these cohomologies at low rank gauge, SU2, SU3 theories, as certain kind of wide quantum black holes in a very quantum ADS-CFT model at finite Newton constant. You know, this kind of question, I think, is not well defined at all, because the notion we have about the black hole is only semi-classical, and we don't know to which extent the semi-classical properties of black holes will extend into the quantum regime. But you know, after you construct concrete cohomology state, you can just play with it and see. And I'll show to you that, if time permits, there are quite intriguing properties in some sense of these small operators which resemble some aspects of black holes. Okay. Now I'm about to briefly present to you the new cohomologies that we constructed during the past 2 years. But before that, to make the statements that I make in the next slides transparently clear, I'll have to emphasize to you one more technical thing, because doing the general studies of these cohomologies is extremely difficult. It's a completely well-defined, even classical problem. You can put it on a computer unambiguously, and you can explain to your mathematician friends unambiguously the problem, but it's really difficult combinatoric problem. So in order to ease these kind of things a bit, very often, though not always, we impose 2 restrictions in our studies. Namely, we restrict ourselves to a certain sector of the n = 4 super Yang-Mills theory. The 2 restrictions that we often impose are the charge restriction and the quantum mechanical restriction. Charge restriction is the following. You know, n = 4 Yang-Mills have many charges, and there are various charge subsectors. You have to construct the cohomology one by one in each subsector. And I want to only study the charge sector, which is guaranteed to contain new operators apart from gravitons. Otherwise, you work hard and just find nothing. And a quick way of diagnosing which charge subsector is guaranteed to have non-trivial new operator is to compute the index of these black hole-like cohomologies only. The cohomology of the index of the full cohomology, both graviton and black holes, there's a nice formula about that. It has been constructed almost 20 years ago by Suvrat, who's unfortunately told me he's ill, and also Shiraz and Maldacena and Kinney. And they have a very simple integral formula, which can be evaluated quite easily, especially at low ranks. For instance, in a fugacity expansion with respect to a charge, a combination of R charge and angular momentum behaving like energy, you can generate a series expansion of this full index very easily. Also, you can compute the index or the partition function or an index of the graviton operators, finite N graviton operators that I explained to you, taking care of all the trace relations. It's not that easy, but we have found certain combination of methods, I mean, using algebraic geometry, using computers and so on, to count these graviton operators with -1 sign for fermions. Once you compute these two, you subtract these, And whenever this number is non-zero in certain charge sector, there's guaranteed to be new operators, at least these numbers of operators. So we only studied these sectors. Okay?
So these don't depend on n?
Which
SU2.
SU2, all depends on n, yes. The first few numbers don't depend on n, but quickly it depends on n and right, yeah. Yeah, for SU2, SU3s and 4s, I mean, you have to do this calculation again. Yeah. So that's the first restriction. We only study a sector which is guaranteed to have new operators and focus on reproducing these numbers of operators. If the number is minus, there are that number of fermion operators. So the threshold level turns out to be 24 in these integer value charges. So it's quite large. So that's the reason why people couldn't find this operator in the simplest SU2 case for quite a long time, almost 20 years. The second restriction that I put is that instead of studying the full cohomology of the Yang-Mills theory, I restrict myself to a quantum mechanical subsector, which happens to exist. Okay? So this subsector, yeah.
You said it, but can you again tell me what exactly is the definition of Z cap? I mean, what you're defining the graviton operators as?
Yeah, just counting these and eliminating all the redundancy coming from trace relations.
Okay, and then when you're taking multi-trace,
yeah.
you're still removing things?
Yeah. So the thing is that some single trace operators are just expressed as a combination of multi-traces. That's eliminated at the first place. So you get a restricted set of single trace operators. Then there are relations among multi-trace operators, multiplying the reduced single trace. You have to eliminate all of them.
Okay. And then how do you get anything extra?
Extra.
So the extras are not of this type.
Or not of this type. Extra are not a polynomial. So multi-trace operators are polynomials of the single trace operators that I explicitly said here. Multi-trace are so extra. Extras are in some sense also defined as a quotient. Quotienting, construct something. If you can make it zero by quotienting with adding these, it's gravity.
So those are all the rest, what you're calling all the
Yes.
rest. The difference is what you're calling the fortuitous.
Yes.
I'm just wondering, I mean, this seems to have everything, right? I mean, why is there anything more than?
This seems to have everything?
Yeah, I mean, why doesn't it have everything?
Oh, okay. So I constructed a Q-closed operator here, restricting the elements to be single trace operators.
Oh, I see.
So by definition, there's no way for trace relation to enter when you check Q-closeness. Okay? So, and then I form a polynomial of them, and trivially they become Q-closed. But for the rest, the Q-closeness has to be ensured by using trace relation.
So you construct a multi-trace operator and then you demand Q-closeness.
Yeah.
And that's not coming from product of Q-closed single trace.
Right.
So those are the rest.
Right. That's right. Yes. Okay. So sorry, this is just finishing the technical part. So the quantum mechanical subsector turns out to be defined by noting the fact that the classical super Yang-Mills theory, defined on S3 times R, it's the radially quantized quantum field theory, that marvelously admits a one-dimensional consistent truncation at the level of equation of motion, classical theory, down to a quantum mechanical matrix theory called BMN matrix model. Okay? It's a magical property of classical Yang-Mills theory. And since our one-loop cohomology problem refers to classical supercharge only, it becomes a consistent truncation of our classical cohomology. It becomes a consistent truncation of our problem as well. Okay? So it excludes many fields and elements, especially excludes derivatives. So the number of independent letters become finite. So it eases the study a lot, although it's quite difficult. So one thing that should be ensured is that even after this truncation, you should be making sure that some interesting states are remaining, okay? And actually we can show by studying the index of this BMN quantum mechanical model that the larger entropy of this model, of this truncated cohomology, should have a black hole-like growth. Namely, when the charges are at the scale of n square, entropies are at the scale of n square. We have confirmed it at a very particular charge regime. Of course, the entropy itself is smaller than the corresponding black hole entropy, because anyway, you truncate something out, but it has a n square black hole-like entropy growth, meaning that many substantial number of states will be retained after these truncations. Okay? Yeah. Please.
just one extra fermionic state at J equals 24.
Yes.
Z minus Z graph.
Yeah, yeah.
It's easy to identify what that operator is in terms of the fundamental features.
You still need to work hard. I mean, now we found it, it's quite easy to confirm. Q closeness is easy to confirm. I mean, once you're given the answer, checking that is not Q exact it's still a pain. Yeah.
Because that will shed light on what I should.
Yeah, just knowing the number doesn't tell you. I mean,
We're just trying to identify what, because J is 24, then R plus capital J will be 4, right? And,
yeah, that's right.
Operators with that, some R and some.
Oh yeah, of course this number constrains the operator a lot. And I mean, I just shown you one fugacity, but you can refine it to many fugacities, and you have a lot of interesting charge data, and that constrains the form of the Q-closed operator a lot. But there are many, many terms. You have to fit the coefficients well to determine it. Yeah.
So what are the total number of operators at this level?
Here.
Yeah.
I mean, the true boson plus fermion.
Yeah, everything.
Oh, I mean, including graviton.
Yeah, I mean, what time is this? You have to start.
Yeah, this index is 7,000 and something.
At least that.
Yeah, at least that one, because it's an index. Yeah. So among the rest, the remainings are, the difference is just all 7,000 something is gravitons. Yeah. Yeah, it's not like black holes at this level because it's just SU2, it's threshold level. I mean, at this level, there are much more gravitons, ironically. Yes.
So in this BMN sector, you're not taking an index. You're looking at all, you're looking at bosons, fermions, everything.
Well, still counting everything is difficult. I mean, still you can count the index within this BMN sector, and I'll compute the difference within the BMN sector.
But the numbers you've given are for the actual...
These ones?
Yes.
I got it from the index, the large N approximation of the BMN index.
Oh, I see. Okay. So even there you're...
Yeah, even if it's a supersymmetric quantum mechanics,
it's still...
if it's at strong coupling, it's not that easy. Yeah, yeah. Yeah, people are doing, these days, I guess numerical simulations to see black holes honestly from here, these matrix models. Yeah, I think enumeration itself also is not that easy at strong coupling. Yeah. Yeah. So this result I got from an index, an integral.
So the truncate, I mean, the fact that it is less is both the fact of both due to truncation and probably the fact that it's an index. I mean, both are reducing it from the expected black hole growth. Is that right? Or
the latter thing, I'm not sure. Yeah. Because we believe the back-engineering working entropy is just counting all the states. But the thing is that I think the second reason is not there. But because at least for the black holes, we got precisely the correct leading formula from the index as well.
From the 4D index.
Yeah, from the 4D index as well.
Yeah. But in the 1D case also you expect that is sort of true, I guess, yeah.
In principle, that's a chance, but I'm not sure whether that will be happening. Yeah, the boson plus fermions and boson minus fermions, whether their asymptotic entropies are different, I'm not really sure. Yeah. Okay.
So the Z minus Z graph for SU2,
yeah.
Do you have some understanding of how these coefficients grow?
Insights on how these grow. Let's say a very large charges.
With very large J, let's say.
Yeah.
So
the full partition function we know because when J is growing very large, we know the exact Hardy formula for the full partition function. Graviton thing, I think we can easily estimate. I'm not really sure on top of my head, but I think we can easily estimate because it's basically counting the polynomial, the large polynomials. I mean, because you're counting this graviton partition function basically with diagonalized matrices. I think you can estimate, but I'm not sure of the precise formula.
Yeah, for example, does it grow like this BMN counting? I'm trying to understand.
The graviton.
Yeah, no, Z minus Z graph.
Z minus Z graph.
So you're saying this is black hole.
Yeah.
Now, is there a, so you can try to estimate its entropy growth with J or something?
I think if J is very large, I mean, this will be much larger than the graviton contribution. When J is very large, even for SU2. So this is counting including everything. But I think it will be dominantly coming from the black hole part. Yeah, I mean,
Yeah.
For large N and a macroscopic J, you would expect that it will grow as Beckenstam.
yes, yes,
That's what you want to.
yes.
But it's
yes.
SU2, so it's not.
For SU2, large, yeah, for SU2,
Yeah.
I don't know how to estimate.
Yeah, but
Are you talking of Z minus Z graph?
Yeah, that's what you want.
That also you think will grow like the Beckenstam?
I think so,
That's
that
because,
goes
yeah, because Z
Yeah,
graph doesn't
at very large energy, Z grav will be subdominant probably. Yeah. Even for SU2, the full index establishes some Cardi-like limit with large J, even at n equal to 2, which looks very similar to the black hole entropy formula. Just blindly plug in n equal to 2 in large N formula. It behaves somewhat similarly. Z grav, I don't know. You have to estimate it separately.
yeah, for example, in this BMN sector,
Yeah.
you have this result that both of them go as J to the power 3/2. So right. So
This one,
at least
this one.
for the small black hole regime. You're
Yeah,
saying.
yeah. This is for the full
but you're saying
index,
this is
full
for-
index in this regime.
Oh, this is for J less than n
Yeah.
square. Okay, so there's
but-
no such regime for SU2.
Yeah, This is for SU2 in the full theory, and SU2 BMN I didn't show you yet. Just to explain to you why it's still interesting to study BMN, I've shown you the larger end result of the full BMN. Yeah, the BMN SU2 I didn't show you yet. It will be more boring, but guiding towards the existence of new operators. Yeah.
Okay.
The SU2 BMN you'll see in the next slide. It's this. Okay. So you can separate for SU2 in the quantum mechanical truncation. It's so simple. Luckily, you can compute everything analytically. The full index you can compute by the integral formula by Souvrat and Shiraz. It's just a simple residue sum. The Z grav in the quantum mechanical sector, you can compute by hand analytically because you're dealing with, one diagonal matrix contains one eigenvalue because they are traceless. So just counting some invariant polynomials you can do by elementary method without knowing any sophisticated techniques. So we compute them both exactly and compute the difference. They turned out to be organizing themselves to this simple expression. I think in SU2 BMN, even if you go to large charge, there might be more gravitons. Yeah, because this is very poor growth, right? Yeah. And that has to do with the fact that we're in SU2, I think, yeah. Let me see. Yeah, probably that's, yeah, right, yeah. So anyway, this gives us a guidance to search for a new class of operators. And this difference between the two indices are organizing themselves into a product of three factors, which individually have very good interpretation. The first factor is what I'll call the contribution from core black hole primary operators. And if you expand it in geometric series, it comes in a single tower. So I'll call this ON, O0, O1, O2, O3. The second factor, I'll have more to say if I have time, but they are coming from the limited dressings by graviton operators. Note that if you have some new cohomology, you still have graviton cohomology, you multiply them, in principle, you expect to have new cohomologies. It's like some black holes dressed by graviton hairs. So this factor is representing that. It comes from the hairs from this single trace, multiplying these single trace graviton operators many times, okay? The remainders are coming from the supersymmetric descendants. This is the subgroup of the full superconformal algebra commuting with our cohomology problem and also commuting with this quantum mechanical truncation. And since this is a compact group, the descendants only generate finitely many terms. So with this understood, the following two factors are giving rise to primaries. Especially these give rise to new operators. And corresponding to each term, index predicts the existence of one single fermionic operator. And we managed to construct that. There's a lot of guessworks and hard works and some systematic works involved, but I'll just present it. Since it's SU2 adjoint, I use the vector notation, which eases the analysis of trace relations. So we found an infinite class of new operators, which is in the non-graviton category. Maybe a bit abusing the terminology, I'll call this a black hole-like homology.
Small f.
Small f is the field strength. The field strength has 6 independent components. Only one component remains BPS. So I call just this f. Yeah.
And these dots and everything are SO6 things?
These dots. Oh no, these dots are
SU2.
Yeah, SU2 trace list matrices are converted to 3-component vectors. Yeah, and this is somehow magically making the SU2 analysis simpler, because basically the only trace relation coming from this SU2 vectors is 2 epsilon tensors being changed into 3 Kronecker deltas, right? So the trace relation analysis becomes much easier in this notation. So the 3-dimensional vectors inner product.
So none of these are SU4, none of these are the R symmetry indices.
R symmetry. So all the indices, and the C, B's, and these are R symmetry indices.
Okay.
So the full R symmetry is SO6. Once you pick a supercharge and define your cohomology problem, only SU3 subset remains, U3. Okay. So these A's and B's and C's are SU3 indices. I mean, rotating the 3 chiral multiplets. Okay? So the index predicts the existence of an SU3 singlet. So we found singlet operator, as predicted by the index. Okay. The most important thing is the lowest operator, O0, which takes this form. This is the operator first discovered 2 years ago by Chiming Chang's group and ours. And if you know the result, it takes ridiculously simple form. 2 scalars and 5 fermions. If you know the details of the graviton operator, this will look like a very strange operator. You know, graviton operator never involved this many fermions. But you know, once you're given this operator, it's just 2-line exercise to show that it's Q closed. Checking that it is not Q exact is a little bit hard. We did it on a computer. Checking that it is not of graviton type is also easy. You restrict all the 2x2 matrices to be diagonal, and you find that this operator is 0. So it is not of graviton type. Okay.
Can you not do some counting and say that supposing you know that this is there at it's a non-graviton operator, this thing, can you not argue that the number of relations that are there, if it were Q exact, because those would be of dimension, you can enumerate, then I'm thinking of what are the linearly independent combinations you can have, and
you mean working out the dimensions of these images and domains and so on? That certainly constrains. That certainly constrains.
But it's not enough. At least for the lowest level, it's even.
Yeah, it's like knowing the. How should I say? It's like just knowing this. What is this? You call it Euler character and the Hodge numbers and so on. Betty number, Hodge number. It's just like knowing all the plus minus combinations of them. It's more like just knowing the index. Something like similar. Yeah.
Okay. I mean, is it that you are calling it non-graviton type because there's a linear combination of single trace or product of single trace operators? Yeah, epsilon, P1, P2, P3. Yeah. Yeah. I mean, I'm just asking that it's one operator, but you can take linear combination of these with any other Q cohomology, right?
Yeah. Maybe of graviton type. Yeah.
So this is not graviton type because you have this linear combination. Is that the point?
Linear combination of where?
Of different multi-trace operators, right?
Oh, these.
The 3 traces.
Not just that, because among the graviton operator, there can be triple trace as well.
Triple trace, yes. Yeah. But here you have to take a linear combination. You take a linear combination, right?
Oh, yeah. Only with this linear combination, it becomes Q closed.
Yeah.
And using the trace relation of SU2.
Yeah. So that's the reason why it's non-graviton type.
Yeah.
I mean, if it was just a product, you would call it graviton type, right?
Yes. If it's just product and maybe just one term. Maybe.
One, yeah.
Yeah.
Even if it was a sum and if it was Q closed by your earlier definition, if it is just Q closed without using trace relations,
you
would call it still
graviton. Yeah, because if you, But the procedure of constructing graviton is first constructing monomials, as Ashok said, and then linear combination, it can be made. Still, I call it graviton. Yeah. But
so I guess the statement here is that this is Q closed only if you use the trace relation.
Yes. The thing is the following. Yeah, if you don't use trace relation, I mean, for general SUN, it will be. I have the operator form here. If you don't use trace relation, general SUN, you can write this as follows. I've just shown you at the last page. You can just take it like this. Trace of any n by n matrix, I mean like this. And this, in the SU2, it reduces, so the final expression is the triple operator trace. Only in the SU2, and in the SU2, I rewrote it in this way. And if you act Q, the structure of this operator is as follows. This is virtually graviton operator. Okay. Part of, this is also, I mean, apart from this traceful part, it's graviton operator. So if Q acts on these, it vanishes. The only non-trivial part is this. This is never in the graviton operator type. If you act Q there here, it decomposes only for SU2 into double trace operators, only for SU2.
Okay.
So the double trace operator is an operator taking this form. I mean, a graviton operator with this form carrying different indices. And using the fact that it's a quartic product of graviton operators and precisely taking this linear relation, it just vanishes. And the trace relation whose Q action of this decomposes into two operators is very crucial for checking Q closeness.
I see,
Yes,
okay.
yeah. So as you say, linear combination is important here, but yeah.
Okay.
Yeah.
Okay, thank you.
Yeah, I think the technical way of characterizing it is this fortuitous versus monotone, yes. Yeah.
So in the full index, the corresponding operator at e to the 24 will be completion of this with extra addressing.
The full index, completion of this
This
with
is the BMN.
yes. BMN computation, yeah.
But then if you go back to the full index, Z minus Z grab that you wrote down.
Yeah, it's also this. Yeah.
There was this -1.
Yeah. This belongs to the quantum mechanical sector, but the remaining things, I mean, only part of them belongs to the quantum mechanical sector. Yeah. Okay. Good. Yeah.
Seminar goes on, so.
Here as well. It's a global convention in India. Okay. But I'll try to wrap up at a certain stage. Okay. So SU3 is much more complicated. I did a similar business, computer difference, but it's much more difficult. I just compute things in series. And again, you can factor it out into three forms: descendants, some graviton hair, and the remaining thing is most important, the core black hole primaries. This is a complicated function whose exact form we don't know. So we compute it in a series expansion form up to 54th power in the fugacity. So it's a complicated numbers. And these numbers arrange themselves into the character sums of the remaining global symmetry group, okay? SU3 subgroup of the R symmetry. So whenever these characters appear in the expansion coefficient, I decide to display them on a table, okay? M combined is the representation of SU3 at given order. And if the representation appears as fermions, I denote the column as fermionic column. If they appear as boson, I call it boson. I deliberately try to align them into towers of operators. I mean, maximally visualizing the coherent patterns of these, okay? So it becomes more complicated, much more complicated than SU2, which was just geometric series. But I think this is going to a good direction, because this is the right direction in which we are generating more states, and there's a hope of getting black hole-like entropy growth, okay? So I don't know the exact answer, but this is what you get for the index. Constructing exact cohomology is much more difficult. At this moment, we managed to just find the representative of the first, lightest black hole cohomologies, and this is as complicated as this. The mechanism in which this becomes Q-close is basically the same as these SU2 operators, okay? First of all, it's dressed by many graviton-like fields, and there are some non-trivial fields. So if you add Q on them, using SU3 trace relation, these non-graviton type operators split into double traces. And these double traces are taking the form of gravitons, which are precisely the same as dressing, like here. So combining all these, it just becomes zero. And the way, we found this complicated thing using the ansatz, precisely in the sense that Loga has asked, taking the advantage of the Q-exact expression when you combine the gravitons and use trace relation, and further forming a bigger polynomial, taking advantage of graviton trace relation, we constructed this. We have checked that this is Q-closed. So for Q-closeness, we have some ansatz to work with, which applies in some cases. Still, checking that this is not Q-exact was a nightmare. One of my collaborators, Xiao Li, Had to use a supercomputer at Michigan for several hours to write down all Q-exact bases and show that the equality doesn't hold. And it's, I have no idea what kind of calculation that is, but they're super strong. So they confirm that this is not Q-closed, Q-exact. So it's quite hard, even after these various restrictions. For SU4, for SU4, we managed to compute the black hole cohomology index when it barely becomes non-zero. We just identified these threshold levels, or we predicted the existence of these new cohomologies, but we didn't manage to construct anything. Okay, so this is technically what we are at, where we are now. Okay. Okay. So sorry for the too many technical things, but just to report where we are. And in the remaining time, I can briefly report to you what kind of interesting features or hopefully physics that we can extract out of these simple new operators that we got. Of course, I'm trying to observe a black hole-like aspects in these small operators. And you may think it's really funny because it's not large n. Yeah. Yeah. And it's not in the semi-classical regime, right? So to what extent they behave like black hole, it's very unclear. We're just going to see some curious aspects out of this operator, which seems to be resembling some aspects that we know about the black holes in ADS. The focal property that I'll be focusing on in the remaining part of the talk is the black hole no-hair theorem and occasionally existing hairy black holes in ADS. So no-hair theorem, if it is true for certain gravitational model, says that the stationary black hole doesn't want to be dressed by hairs of gravitons or matters outside its horizon, but it rather wants to absorb it. Okay? This theorem holds in certain models of gravity, coupled to certain matters and so on, but it is violated very often. It's violated in an interesting way. If you have certain charged matters to it, or if you put it in an ADS and both and so on. When it is violated in a very interesting way. For instance, the violation of the no-hair theorem in ADS black holes or black brains is linked to the existence of an interesting holographic phases of matter, like the holographic superconductor or superfluid that has been first explored by Gobser in terms of black brain solutions. And in the hair that exists in this black hole or black brain solutions appear for the modes that are holographically dual to the order parameters that are characterizing the phases of these holographic interesting matters. So the no-hair theorem's violation has very interesting physics. I also like to emphasize that the no-hair behavior and the hairy black holes behavior is not completely mutually contradictory or exclusive to each other, because this is kind of mode-by-mode question. If you have a black hole, you have matter fields or graviton outside. These given fields have various modes in the outside of the black hole. Some modes where you want to condense and exhibit non-zero values as a hair outside black holes, while other modes do not. Okay? It's related to the sign of the imaginary part of the quasi-normal modes outside the unhairy black hole. If the imaginary part of the frequency is, I think, negative, right? Is positive, negative, then the quasi-normal modes decays, wanting to be absorbed into the black hole. If the imaginary part is positive, did I say positive? Positive, it exponentially grows in time, wanting to drive these unhairy black holes to a hairy black hole, right? So it's a kind of mode-by-mode question. So I try to explain to you a kind of partial no-hair behavior of the operators that we construct in these low-rank gauge theories. Okay? So let's start from the simplest SU2. It might sound ridiculous, but this SU2 model and example that I worked out seem to be showing us very rich physics concerning the subject, hairy black hole subject that I mentioned. To really emphasize this, we start from the SU2 theory at the BMN quantum mechanical sector, to be simplest. I've explained to you the three factors, especially two factors attributed to the core black hole operator and the limited class of gravitons that can be dressing them. Index is seeing these kind of product operators, right? But recall that if you have a black hole-like or non-graviton cohomology and the graviton cohomology, in principle, multiplying any of them give you another cohomology class, right? Because the multiplication remains to be Q-closed. So the fact that the multiplication of the other graviton particles don't appear in this index seems to imply something non-trivial. By the way, it turns out that in this quantum mechanical subsector of SU2, there turns out to be 17 different kinds of single trace graviton-like operators. Out of that, only three are allowed to multiply the core black hole operator in the index. Other multiplications are just not seen. And jumping ahead a little bit, there's various scenarios to explain the non-appearance of these kind of product operators for the remaining 14 of them. But if the index doesn't capture these product operators, one natural possibility is to conjecture that they just don't exist. Okay? So that kind of hair, those black holes don't like that kind of hairs multiplying them. Okay? And the way they don't exist in this supersymmetric.
Then Z minus Z graviton will be the black hole index times the hair index.
Yes, yes, because if it's a black hole index times a hairy index, it's not a graviton index. Yeah, right. Yeah. So in a broader sense, it's included in the black hole index. There may be non-hairy black hole and hairy black hole. Yeah. So the way in which they can be absent, despite its naive presence, is that this operator after multiplication is becoming Q-exact. Because in the cohomology, Q-exact operator is nothing, and it's not in the BPS spectrum. So that's one scenario, right? And we have explicitly checked it for some low-lying product operators. So these operators not appearing. We have explicitly checked that for the smallest black hole, so-called black hole operators, and some light graviton operators. Each of them are cohomologies, but after multiplying them and using extensively the SU2 trace relation, they turn out to be trivial operators, Q of something like that. So naturally explains why these products don't appear in the index, because they are absent in the cohomologies. Okay? And we are having in mind a scenario, I mean, it may not always be true, but many of these product operators not appearing in the index, we have in mind a scenario that they may be absent in this full spectrum. Okay? So it seems that this quantum mechanical index is exhibiting a strong partial Néel phenomenon. In most of these graviton, it doesn't want to be dressed, only except for these three. This curious aspect generalizes to the full SU2 index. This is the only moment I show you the non-quantum mechanical full SU2 Yang-Mills theories index, the difference between the two. Because the graviton index without this quantum mechanical truncation has been computed numerically on a computer. We did computation up to 40th order, and the difference can be explained in a very curious manner. Okay. This is basically the number that I've shown you before. It's like the, full SU2 index. Now I'm showing you the more refined version of that. I refine with more chemical potential for internal symmetries and spin symmetries. And in order to ease your view, I arranged many of them into certain characters, okay? The first part is the character of the underlying superconformal symmetry group in the cohomology problem. All the operators turn out to be in the same supermultiplet, luckily, so I factor out the same character. And the remaining terms in the square bracket are all parameterized, all representing a primary of its own multiplet. First term is the threshold black hole-like operator. And naively, if these operators could, so the discussion of the possible graviton hair can be divided into whether the graviton operator is conformal primary or conformal descendants. The two behave quite differently. And that will have impact on the gravity dual calculation as well. So for conformal primary operator, just extending these results, there turn out to be 32 graviton cohomologies, but out of them, 29 dressing the black hole operator don't appear. Only these 3 dressing the black hole appear in this term, okay? So that's the reason why you see this big gap between the threshold level and the first hairy black hole operator, product operator level. So this big gap explains the fact that the conformal primary gravitons, the black holes don't like to be dressed by them, with the exception of these 3. I don't know why these 3 operators are so special, but that's what we observe. Mostly conformal gravitons, not carrying the wave function orbiting factor, black holes don't want them to dress them. This operator don't want them to dress them. After this level, appearance of this first Harry operator, there turns out to appear many terms. And all these terms can be accounted for as by the product operator of this and the conformal descendant graviton operators. We haven't constructed the cohomology explicitly, but every term can be explained in terms of these Harry operators. Okay? And they're all conformal descendants, and it means that the co-operator wants to admit the multiplication of many conformal descendants carrying orbital angular momentum, I mean derivatives. This is what we observe in the SU2 theory, and that will seem to have a very natural qualitative analog in the black hole duo. So now I have to decide what to say and what not to. I initially prepared a very grand talk, although it's a cohomology talk. Oops, what's happening? Yeah, although it's a cohomology talk, I thought it would be better. I mean, although it's all about cohomology, BPS states, and BPS black hole, I thought it would be better to have a slightly broader view about what the status of general Harry black holes are in ADS 5 times S5, supersymmetric and non-supersymmetric, because there has been such studies from quite a long ago, 10, 15 years ago, often led by Shiraz Minwalla, and before that by Oscar Diaz, many people. But from last year, I have worked with TIFR group and some of my Korean colleagues on this problem again. We seem to find, we happen to find many more Harry black hole solutions, BPS and non-BPS. So I think it will be interesting to leave a few remarks on this to provide you a broader view about this Harry black hole business than the BPS cohomology that we are discussing. And knowing this structure will lead us to a better direction on how to study, which kind of cohomology to study and so on. So I'm going to give you a little bit of broad overview. Okay, I think I can. So first black hole that I'm going to study in ADS 5 times S5 are non-Harry black holes. They're taking the form of Kerr-Newman black holes in ADS 5 times S5. They can carry various electric charges and various angular momentum. But for the simplicity, I take all the electric charges to be equal. Okay? Call it R, because in this talk, Q is supercharge. R for R charges, for instance. Yeah. And they call the angular momentum J. And you also have an energy for non-extremal black holes. So you have 3 charges. So to explain the properties of these Kerr-Newman black holes, it's helpful to plot some important properties of these black holes in a 3-dimensional charge space, R and J and E. Okay? So in order to help visualize things, I plot a 2-dimensional slice of this 3-dimensional diagram with fixed electric charge. R equal to 1 is certain convention, ADS radius set to 1, and charges defined by multiplying Newton constant and so on. And with charge fixed to certain level, I draw to you various important lines in the angular momentum and the mass energy space. Horizontal is J, vertical is E. I want you to focus on the 4 important lines. First line is the gray line here, all the way to the middle here. This is gray in between. This gray line is the extremal black hole line for the Kerr-Newman black hole, temperature being 0. So this Kerr-Newman black hole exists only above these gray lines. Okay? The second line of interest is the dashed line, which is the BPS unitarity bound line, energy being equal to the linear combination of electric charge and angular momentum. Okay? Any black hole sitting on this dashed line is BPS. Any black hole, no black hole or no states can exist below this dashed line because it's kinematically forbidden. Okay? It turns out that the extremal black hole line and the BPS bound line tangentially meets to each other at a point at which there is a BPS black hole, only at this point. In general, extremal black hole and BPS black hole are different. Only at this place, there is a BPS black hole in ADS found 20 years ago by Gutovsky and Real. If you extend it to a 3-dimensional charge space, this point extends to a 1-dimensional line. Okay? So this is a locus of the BPS black hole. 2 more lines are of interest in this talk. So since the black hole has charges, it has a conjugate chemical potential, and conjugate to the angular momentum, there's an angular velocity. Okay? And if either this chemical potential or angular velocity is larger than 1, the black hole is known to be unstable, known or believed to be unstable, both dynamically and also thermodynamically. Dynamical instability means that some quasi-normal modes are exponentially growing, driving it to some Hairy configuration. Thermodynamic instability, if I say it very crudely, means that when mu is larger than 1, you try to emit some matter carrying energy and R charge, and electric charge, and that by this way you increase the entropy. Okay? And since emitting the charged hair increases the entropy, the original black hole is thermodynamically unstable compared to the Hairy configuration in the microcanonical ensemble. Similarly, if omega is larger than 1, you try to emit the states carrying large angular momentum, carrying E and J, roughly satisfying this relation, after which you get entropy increased. So the black hole thermodynamically once prefers to emit these matters with these hairs with large angular momentum. Okay? So it's important to know which regions which regions they are in this plot. So the mu equal to 1 line is here, red line, and below this mu equal to 1 line, between this red and gray line are the mu larger than 1. So Kerr-Newman black hole is unstable against the emission of electric hair in this region. Here, omega equals to 1 in this blue line, and below this line, omega is larger than 1. So between this blue and gray line, sorry, so narrow, Kerr-Newman black hole is unstable against emitting some hairs carrying spins. Okay? There are, of course, regions between this gray line and the dotted line where no Kerr-Newman black holes are existing. But anyway, we consider two regions. The regions 1, below the mu equal to 1 curve and the BPS bound, and the region 2, below the omega equal to 1 line and the BPS bound. And in these two regions, this region and this region, two distinct classes of Hairy black holes has been discovered. One is basically on the archive now. One is to appear, I hope, soon. So in the first regime, the Hairy black hole constructed is a black hole surrounded by a thermal gas of gravitons carrying extra angular momentum. We call it gray galaxies. So the characterization of that is it carries large angular momentum. And in the region where mu is larger than 1 or below that, the characterization of the Hairy black hole is the hair carries large R charge or electric charges in the form of coherently excited chiral primaries. And these are coherently excited in a way that they are represented in the gravity dual as a large dual giant graviton, a D brane extending in ADS, basically surrounding the core black hole inside. Okay? This is the kind of exotic hair that we have discovered and spans the Hairy black hole configuration in the second regime, no matter whether the Kerr-Newman black hole exists or not. Okay? So this is the kind of two hairs that we have been establishing over the past 2 years. And both regions extends down to the BPS line, so it will have strong implications to the BPS black hole, Hairy BPS black hole, and our cohomology problem. That's the reason why I was mentioning this. All you have to remember is that the first region, the hair carries large angular momentum. Second region, it's more exotic. It just carries electric charge, and it's realized in the form of brains. Okay? So the first case where we have rotating hairs, the SU2 cohomology already shows an aspect very similar to that. I've shown to you that the conformal primary hairs are almost disallowed by SU2. Conformal primaries are those which don't carry angular momentums, right? Basically. But many descendant hairs carrying angular momentums are seen by the index. So already this seems to be very similar to what we have been finding in the previous slide in terms of gray galaxies. So we can really rigorously check that by doing a calculation in the supersymmetric sector, by studying the possibilities of hairs in the BPS black hole background. Okay? And skipping a little bit more detail, we have really shown that the perturbative hairs of these scalars is disallowed when the angular momentum carried by this scalar field is lower than a critical amount specified by the size of the background black hole. While the regular hairs are allowed when the angular momentum carried by this mode exceeds the threshold value characterized by the black hole size. So the regular hairs are only allowed for highly enough orbiting, descendants. but not for conformal primaries. At least qualitatively, this seems to be very similar between large N gravity calculation and the SU2, this trivial, small cohomology calculation. It seems to be more impressive agreement than we deserve to expect. So I think it's a very nice thing to observe. And intuitively, if you look at the gravity calculation and think about, instead of this one, think about a heavy chiral primary and doing the same calculation. For heavy chiral primaries, you can semi-classically do this Hare calculation by computing this heavy particles orbit, okay? So in order for this heavy particle orbit to stay outside the black horizon, to be a Hare visible to the outside observer, it should rotate fast enough for its orbit to stay outside the horizon, okay? That's the intuitive reason why the Hares are, in the wave picture, Hares are allowed only for highly spinning descendants, okay? So having all this in mind, and having noticed that quite similar phenomena are discovered in this SU2 cohomology problem, we can conjecture or claim that even for SU2, these Hares dressing these small operators O0 sort of see the quantum horizon of these new operators in a very curious way. Depending on whether the multiplication become Q exact, trivial or not. So I think this is a very nice observation, and it deserves to be studied further in the future, I think. Yeah, although it's all qualitative. Yeah.
Yeah. Somehow one would have expected that when you go from strong to weak, the actual description of the states will be modified drastically, right?
Yes, that's true.
This is not happening.
The actual shape of the state will be very, very different. But this cohomology is basically giving the existence or non-existence.
Yeah. But the mixing, the states will all mix with each other, right? So what you think of as
rather than this simple product.
Yeah, exactly. What you are thinking of as graviton state versus black hole state,
they'll definitely mix. They'll definitely mix. This is the deceptive simplification of this cohomology, because in cohomology you have two cohomology and multiply them. That's a representative of cohomology. But the actual BPS operator, even at one loop, the actual BPS operator, which is different from this by an addition of Q exact term, presumably will violate this factorization structure. So, this is a deceptive advantage, technical advantage of, you have your right to choose your simple representative.
That's true, but somehow it's surprising that on the macroscopic side, you still have a product structure, right? Because you have a black hole and the Hare rotating around the black hole.
Yes.
That seems to give a product structure.
You mean in the gravity side?
On the gravity side.
Yeah. And saying that if you reduce the coupling that is broken.
But again, it's restored exactly in the weak coupling.
Yeah. Maybe this representative is clever enough to say something deep about the gravity, though I don't really know. I don't really know. Cohomology, if you choose a nice representative of cohomology, we know in many examples that it retains some robust aspects as coupling change, like the chiral rings and so on. It'll be good to have a good interpretation why this can happen at recoupling, but it sounds quite miraculous in some sense, yes. Okay, I'm badly running out of time. So this first class of product operators or Hare operators I explained, and the kind of Hare operators I explained to you was the following. In the gravity dual, these kind of product cohomologies seem to be realized by having a black hole and the Hare given by a wave function of a particle, sprinkled outside the event horizon. Now the second class of Hare is utterly different from this, because I explained to you, quoting the work in progress, that the second class of R-charged black hole, electric charged black hole, is a large brane, dual giant gravity wrapping this core black hole. And that's a very different kind of Hare. So how could you realize this Hare? This is some speculation or work in progress. I'll skip all the details, but if you stare at the black hole core cohomology table in the index, we seem to have lots of towers, and the simplest tower is this. And the rough idea of trying to identify this as a dual giant graviton tower is that if you have a black hole core, and I have a dual giant graviton dressing that, it may have a larger and larger radius, okay? There may be some families of towers with the brane's radius being larger and larger. And this is naturally interpreted as this tower appearing here. And to generate this tower, you have to include more and more scalars, completely symmetrized. And that's the structure that the dual giant graviton satisfies. And if you work out all the charge structures, it has the right structure to suspect that it's given by the following operator. So this is the last thing. This will be the last thing. Sorry about taking too much time. So in order to construct this kind of hairy operators, you have to know one very odd property of dual giant graviton. It's a D3 brane, three-dimensional brane, 3 plus 1 dimensional brane, occupying a sphere in ADS5. So it acts as a domain wall of an RR5 form flux. If you cross this D brane from outside to inside, the unit of RR flux reduces from n to n minus 1. So if there's a black hole in the inside, the black hole will feel as if it is dual to a microstate in an SUN minus 1 theory, in some sense. Okay? So the core black hole, so if you start from SU, that's why I started from SU3 theory, because if you had started from SU2 theory, have dual giant graviton, inside you'll have an SU1, then there's no meaning to construct a black hole cohomology for SU1. So for starting from SU3, you have some dual giant, and inside that, you suspect that there will be an operator which takes the form of an SU2 cohomology, SU2 threshold operator. So it's roughly kind of product of an SU2 threshold operator that I've explained to you. But it cannot be a direct product like this way. It's not a particle, it's not like this, because first of all, this is not Q-closed. Although I said that inside the dual giant, the effective gauge group reduces from SUN to SUN minus 1, the cohomology has to be phrased completely within SUN language. You have to use 3 by 3 matrices. And if you add Q on this product cohomology, this factor is just non-zero. So this is an illegal operator. It's not representing the dual giant wrapping a core black hole. So in a sense, my ansatz, work in progress, is to work with these letters and work with an operator with this shape, but you have to gauge contract these indices in a non-factorized manner. Maybe entangle the gauge indices of these two factors in a complicated manner to make it Q-closed. So probably if you work out this, you may have a good notion about what is the gauge theory signature, group theoretical signature of having a brane wrapping a black hole, which I think is quite nice. So this is something that I want to do. I can say it's a work in progress. So I ran out of time very badly. So by just showing the last slide, I will finish. Thank you very much. And sorry for going over time.
So regarding this last statement, let's say if I started with SU3 and I went on the Coulomb branch,
SU3 and what?
And went to the Coulomb branch where I got an SU2.
Coulomb branch.
Yeah.
Yes.
So then, I would, so there should be a way of writing the SU3 operators, on the Coulomb branch.
Oh, you want to rewrite this in a way that the U1 dual giant and the SU2 core is better visible.
Yeah.
Yeah, I think I have that strongly in mind in constraining my ansatz, because suppose I got very complicated SU3 solution, and then you may restrict yourself to all the matrices to a block diagonals, SU2 times U1, and see how these operators behave. Yeah. Maybe if the operators factorize or something.
No, I was thinking more like, if you think of this as some Higgsing,
yes,
if you're going out in the Coulomb branch,
yeah,
then it might be that, that you are kind of writing the SU2 operators as some, Higgs version. You start with the SU3, and then you take some commutators with the phi's in a way that, if you effectively give some wave to one of them, it just becomes an SU2-like thing. Is that the kind of operator, would that, is that something that you think might work? Or, not just taking the product of SU2 guys, but maybe, just dressing it with some phi, some Higgs things, one of these phi's, taking a commutator or something such that when you take phi to be like some 0, 0, 1, okay, in SU3, you get something which basically looks like SU2,
Yeah, but the operator has to be constructed in full covariant language.
Yes.
I think by going to Higgs branch or Coulomb branch, that kind of SU2 structure should be visible if we have constructed the right ansatz.
Yeah, exactly.
I think that should be the right structure to pursue, I think. Yeah.
Yeah.
And that will probably constrain the form of the correct operator, I think. Yeah.
Yeah.
So you take the threshold operator that you showed for SU3,
Yeah.
then go to some block diagonal form and then see if you can get.
No, that's not the case. That's not the case. You know, the threshold operator for SU3 just happens to have the same charge as this. Happens to have the same charge as the SU2 threshold, but it takes a very different form.
In that, if you take a block diagonal form for the matrices,
No.
say that you have separated one thing.
No. That doesn't happen. That doesn't happen. You know, if you dress it by certain hairs, if you dress an operator at this charge level by some scale hairs, you should have larger scale dimension. So it's this. I mean, the charges completely match with these. Yeah. So this is the SU2 threshold. I mean, charge-wise, it correctly agrees with the SU2 threshold operator, not SU3, dressed by 3 scalars. Yeah. So using this SU3 scalar and Higgsing, I mean, I don't think it'll be getting to the dual giant gravity. Yeah.
So I have a question, actually. It's about the this last question. I mean, the question about, no, sorry, not on this slide, but.
Last slide?
Yeah. I mean, you talked about the quantum horizon.
Yes.
At finite n. So I have a suggestion for you.
Yes, please. Yes.
So if you take, for example, this goes back to the work of Shiraz and collaborators on the plasma ball.
Oh, yeah.
So suppose let's take SU3 gauge theory, okay?
Yeah.
And let's look at a finite region of the deconfinement phase. So there's a phase boundary between the deconfinement and the confinement phase, but it's not a sharp boundary because n is finite, actually.
Yes.
So that's a complicated thing, but we can imagine it exists, actually.
Yeah.
So now, if you knew how to do the ADS-CFT correspondence at finite n, then I think you would know what is the meaning of a quantum black hole or a horizon which is not sharp, which is the case when n is equal to infinity. I just wanted to share this thought.
Yes. I mean, the plasma ball studies are, I guess, made using hydrodynamic analysis and so on.
Yes, but that, of course, was done at large n.
That was at large n.
At large n, they made a connection between the plasma ball as a classical solution of the large n gauge theory and the black hole and another soliton as solutions of the Einstein theory with G Newton going to 0. I am saying that suppose we take this idea and try to implement it at finite n. We understand the gauge theory, in principle, and we can talk of a deconfinement phase and a confinement phase with a phase boundary which is not sharp now.
Start from certain operator and try to identify which region.
Yes, because one of the important things they did in that paper was to identify the phase boundary with the horizon of the black hole. So
I see.
I am just saying that.
I see. With that in mind, I'll try to definitely
quantify.
Quantify what I said.
So difficult part is to understand the correspondence at finite n.
That's right.
Yeah. Especially at finite temperature.
Yeah, that's right. I mean, the thing I presented is very limited because, you know, I've only tried to identify this horizon, whatever, using some stationary probes only, strictly staying BPS. So maybe deforming this away from BPS a little bit more, I can get more dynamical lessons.
Awesome.
There are some things I can try, I think. Okay. Yeah. Thank you very much.
All right.
Are there any more questions? If not, then let's thank the speaker once again.
Thank you very much.